Did you say for HF band?
Is there any digital modulation techniques you can use in the HF bands?
Lots of.
Yeah. Basically all the digital modes you can use in the HF band.
Mhm.
There are variations of frequency shift keying and phase shift keying and combinations of those. Most of the digital modes are either phase shift or frequency shift.
Mhm.
Even the old ones like Pactor.
Yeah, I don't know that.
There's probably at least 40 or 50 that are used.
You can do TV too.
Yeah.
Low scan.
Slow scan.
Almost like fax.
Did I start?
Yeah, you store it.
Digital
Okay.
modulation.
All right. Keying defects, overmodulation, digital codes, and spread spectrum. I knew it was in there somewhere. Took me a while to figure those out. I'm not sure I still have it figured out. I understand more about it. The biggest problem sending CW is key clicks, which we talked about, which generates spurious signals because you're sending extra harmonics. So that's why you shape the signal, increase the rise and fall times, or do the shaping to get rid of those harmonics. It says modern transceivers. I'm gonna have to check. Of course, I've never done CW, so it says I should be able to set the rise and fall times on my radio. There's probably a menu in there somewhere. You haven't done it, right? Change your.
No, you can go in and you can modify. I mean, you can modify the length of the dit and the die, and
Okay.
but
That's
I'm
part of
not-
the auto keyer, right?
Yeah, but I'm not gonna do it unless I am annoyed with it. I think the only thing I did is I might have gone in and reverse keying so that on a paddle it's
Yeah.
opposite
Yeah.
but I don't mess with
Okay.
the shape of it or.
So the ARL recommends
Yeah, no.
at least a 5 millisecond rise and fall time on the signal. I don't know what's standard on the radio nowadays. This is showing your standard keyed waveform and what the rise time would be, and then what it looks like when you basically do the trapezoid, which gives you these slower rise and fall times. Or if you apply the raised sine to it, and you get about the same thing as the trapezoidal, except you get a little more rounding at the top, so it's probably a little less harmonics coming out. So what's the primary effect of extremely short rise or fall times on a CW signal?
Charlie.
Have a good day.
What's the most common method of reducing key clicks?
Alpha.
Okay. To ensure high quality signals, doing audio frequency shift keying, such as PSK31, you really need to control the audio input, or a lot of times they'll define it as the microphone input, microphone gain. That's a common cause of overmodulation, and it generates more harmonics and spurs and other bad things. So if you're trying to determine if you're using excessive input, you measure the intermodulation distortion of the signal And they say that for an idling, I guess, non-modulating signal, it should be minus 30 dB. I'm not sure what you measure it with. You have to get out a spectrum analyzer or actually do a test. Because I thought intermodulation distortion you did with the two-tone test, right? So anyway, what's the common cause of overmodulation of audio frequency shift keying signals?
Over delta.
Delta.
What parameter evaluates distortion of an audio frequency shift key signal caused by excessive input audio levels?
Delta.
What is considered an acceptable maximum IMD level for an idling PSK signal?
Delta.
Okay. Normally, everything today uses ASCII or what also called Unicode. We used to use Baudot code, particularly for RIDI. Although, I don't know, if you do RIDI today, is it still doing Baudot or is it doing ASCII? Since I've never done RIDI.
Interesting question.
I tried it once and I didn't get anywhere.
Probably Baudot, because you limited to number of symbols. Really, it's all calf.
Right. And so is Baudot,
Yeah.
unless you do the extra bits to shift.
And that allows every.
Pretty much. So basically, Baudot is a 5-bit per character representation, where ASCII is 7 or 8 if you include a parity bit. ASCII does the entire upper and lower case punctuation and numbers, where Baudot only uses capitals. And I don't know how you do the shift code on Baudot, but in order to get some of the other letters or figures, you can do some kind of shift code.
That's only a few extra symbols besides the caps.
There's your standard ASCII code chart, which is in a hexadecimal format. And you can see basically everything is there. What was that, Byron?
Just about the whole top row is not in RIDI or Baudot.
Yeah, those are all, the special symbols.
Some of the other symbols on the well either.
And most of those aren't in Morse code either, right? And here's the Baudot pattern. And you see it's only A through Z and a couple extra things, which I don't know what they are.
One of it's spell,
Okay.
and I think the other one's flying through the chart.
All right. That makes sense. By Emile Baudot, 1888.
It reminds me of the paper tape.
Yep. Started off with paper tapes. That's how we loaded information on the Apollo guidance computer. What are some of the differences between Baudot and ASCII?
Baker.
What's one advantage of using ASCII?
See,
I think also ASCII allows async, right? Baudot doesn't provide us the timing or synchronous.
Well, it's not in the ASCII code per se, but normally on a serial interface, you have a start bit and a stop bit. But you could do that sending Baudot too. What's the advantage of including parity bits in ASCII characters?
Delta.
Spread spectrum. Says it was developed 50 years ago by the military, kept a secret. Because it's resistant to noise and interference, jamming, and unauthorized detection, because unless you have the code, you can't decode it. I think as far as I know, the newer cell phones, the 3G, 4G, 5G are all basically spread spectrum techniques. And now the amateur bands above 420, you're allowed to use spread spectrum. I don't know if you heard anybody around here doing it.
I've never heard anyone. Some of the digital modes, that you can get in your software package that works HF are actually spread spectrum that are not legal in the US or legal in Europe.
Okay. For HF.
Yeah.
But you could use it above 420.
Yeah.
The downside is spread spectrum because it's a wider spectrum, takes up more bandwidth. So we have two kinds, frequency hopping spread spectrum, or FHSS. One example is the Wi-Fi band, the ISM2, which is industrial, scientific, and medical, or something like that. But it's basically the public 2.4 gigahertz band. And they divide that up into 79 1 megahertz channels. And they have these 22 different pseudo-random sequences that they can use. So it picks one. Of course, the receiver has to also know which one of the sequences is being used. And then as it transmits, okay, it follows that pattern and hops about 2.5 frequency hops per second. And it may go through all 79 channels in a transmission. So those patterns determine how many of the different channels are used and how often. So it makes it very hard if you don't know the pattern in order to receive it, because you're just getting lots of wideband noise. And they normally use the Gaussian frequency shift keying, which is just another modulated waveform. You use a Gaussian filter. It's kind of like doing the sine or cosine shaping. It uses a Gaussian filter shaping, which rounds the the waveform off so that you get rid of some of the harmonics. And it supposedly makes it easier to decode it. The other one is direct sequence. And it takes this 11-bit Barker sequence. And I don't know how many different combinations make up the 11-bit sequence, but it uses one of those, and it uses that to modulate the waveform. So basically, you're sending out 11 bits for every 1 bit that's in your signal. So it's going to make the spectrum like 11 times wider, which is kind of where it got its name. It uses binary phase shift keying, where the other one used the Gaussian, it was frequency shift, right? And then the binary, you've got both phase and amplitude information. So it definitely requires a linear amplifier to do it. But you can't do it with a Class C amplifier because of the amplitude information. So how does spread spectrum technique of frequency hopping work?
Delta?
Delta. Now, what I don't know like if you use it for amateur communications, how you sync up the transmitter and receiver.
Yeah, I was kind of wondering the same thing myself.
For radio control, you actually bind the receiver and the transmitter together, and that's where they use the same pattern. But if you're doing it over the air, I don't know how you do that. Because it's got to know, or else you can't decode it. And you can't just send it. Anybody would get it.
No, because it takes some time to decode every one, because you'd have to go through the possibilities. Yeah,
You had to have some type of acquisition scheme to acquire the signal and lock to it.
Yeah. Yeah, I don't know how that part works. But it's not part of the exam, so you don't have to know either. What spread spectrum communications technique uses a high-speed binary bit stream to shift the phase of an RF carrier?
Let's see.
Right. Because that one's phase shift, the other one's frequency shift. They're both designed to be resistant to noise, interference, jamming, and unauthorized detection, which is how they were originally developed. And I assume the military still uses that technique.
well, it's
Um,
hard to detect. So
yeah,
the enemy's not going to see a signal sitting there at one. It's anti-jam because in order to jam it, you would have to be hopping along in that sequence.
or just blast everything, broadband,
So,
megawatts.
yeah, so it's very effective at maintaining communication in a battlefield.
So it's more resistant to narrowband interference, because it's effectively very wideband. It requires a higher or uses a higher data rate. So it's more expensive because it costs more to send or to generate higher data rate signals. And they claim that if you're not using a spread spectrum or the spread spectrum algorithm, that the signals are suppressed. I said rejected. They basically aren't decoded. So I don't know that it actually suppresses them more than ignore them. So why are received spread spectrum signals resistant to interference? Because they think they're suppressed. Okay.